Hi, my name is Mark Rulo. I'm one of the mathematics consultants in the Learning Success Center at Mount Wachusett Community College. In this video, I will explain confidence intervals. This comes from Chapter 6 in your statistics class. First, a review. Let's say we're interested in the lengths of fish in a lake. We can speak of the parameters of this population, which will be represented by this large circle. These parameters include mean, abbreviated with the lowercase Greek letter mu, variance, represented by lowercase Greek letter sigma squared, standard deviation, represented by sigma, proportion, which is a lowercase p, size, with a capital letter N, and so on. Because it may be impractical or impossible to measure each individual fish in this population, we might try to describe the population based on a sample, represented by this smaller circle. The sample also has certain parallel statistics associated with it, including its mean, abbreviated x bar, variance, which is lowercase s squared, the standard deviation, which is s, proportion, represented by p hat, size, which is lowercase n, and so on. Let's say that the population is normally distributed. If I take a sample of fish and measure their lengths, that sample mean can be quite close to the population mean, but it can be a bit smaller or a bit larger. But if I take a lot of samples and average them out, I would find that the mean of the sample means would equal the population mean. Now if I look at that population distribution, there's a region down here which represents the smallest 10% of that population. If I catch one fish, there is a 1 in 10 probability that the fish I catch will be from this region. But if I catch 3 fish, then there is a 1 in 10 times 1 in 10 times 1 in 10, or 1 in 1,000 chance of catching all 3 fish from this region. It works out that the standard deviation of the sample means equals the population standard deviation divided by the square root of n, our sample size. A distribution of sample means will look something like this. It's much narrower than our population distribution. In other words, it's much easier to catch one small fish than it is to catch a sample of 3 small fish, and it's harder still to catch a sample of 10 fish all from this region. If I catch some fish, I can calculate that sample mean by adding up all the lengths and dividing by the number of fish I caught. For example, let's say it's 15.5 inches. I might suppose that the true population mean is close to that, but I can never say with 100% certainty what the population mean really is, unless I caught and measured all the fish. But I can construct a confidence interval of the population mean. I could say, based on my statistics, that I have, for example, a 90% confidence that the population mean is within a certain margin of error, E, of the sample mean, x bar. For example, if x bar was 15.5 inches and E equaled 3.5 inches, then we could give a 90% confidence interval range of x bar minus E to x bar plus E, or between 12 and 19 inches. If you weren't satisfied with a 90% level of confidence, you could raise that level of confidence as high as you want, 95%, 99%, maybe even 99.9%. But the higher your level of confidence, the wider the confidence interval gets, and at some point, that wide interval becomes almost meaningless. When the population is normally distributed, or if n is greater than or equal to 30, we calculate the margin of error for the mean one of two ways. If sigma, the population standard deviation, is known, then we use the standard normal distribution, and the margin of error, E, equals ZC times sigma over the square root of n. ZC is called the critical z-score, and you can find out how to get that value from the video I made on how to use a z-table. As a quick summary, a critical z-score is the value of that z-score which, along with its negative, symmetrically brackets a given level of confidence about the mean. For example, if we want a 90% level of confidence, we are looking at this area here. The area of 90% is in the middle, which leaves 10% in the tails. Half of 10% is in each tail, or 5%, and we can use the z-table to find the z-scores that give us 5% in each tail. The critical z-score is always given as a positive value, though it really represents the positive and negative values of that number. In this case, that comes out to be 1.645. In method 2, if sigma is not known, then we use a t-distribution to find the margin of error, and that formula says E equals Tc times S, which you may have to calculate, over the square root of n. Tc is a critical t-score, and that can be found by using a t-table. A t-table can be found at the back of your book and can be found online, including in the Learning Success Center's LibGuide site. As we are using one variable, we say that we have n-1 degrees of freedom. If we had a sample of 14 and a level of confidence of 90%, we would go to the t-table, find 14 minus 1, or 13 degrees of freedom, and go over to the column with 90% level of confidence. The critical t-score, in this case, would be 1.771. Note, the column for degrees of freedom in the t-table in the book does not have every natural number, but online t-tables may be more complete. If necessary, though, you can use the closest number of degrees of freedom that is smaller than the one you are looking for. For example, if you had a sample of 58 and could not find a t-table that included 57 degrees of freedom, you could use the row for 50 degrees of freedom from the t-table in your book. Also note that as your degrees of freedom gets bigger, the critical t-score gets closer and closer to the critical z-score for that level of confidence. Once you have your critical z-score, or critical t-score, it should be straightforward to calculate your margin of error, and then to construct your confidence interval. The low end of the interval is x bar minus e, the upper end is x bar plus e. We can also rewrite the formula for margin of error and solve for n. That is, for a given margin of error, sigma and zc, or margin of error s and tc, what is the smallest sample size needed? In these types of problems, always round up. For example, 17.3 fish becomes 18, because you can't have 0.3 of a fish, and rounding down to 17 means not quite reaching the level of confidence given. If you are calculating the confidence interval for a population proportion, you'll first need your point estimate, which comes from your sample. For example, we want to know the proportion of fish in the lake that are smaller than 15 inches. This is a question about a population, but again, we cannot catch and measure all the fish in the lake. So we take a sample. Let's say that in our sample, we catch 82 fish and that 37 are smaller than 15 inches. Our sample proportion, called p hat, becomes x over n, or 37 divided by 82, which is 0.451 to 3 decimal places. Q hat, then, is the proportion of fish that are not smaller than 15 inches, and that equals 1 minus p hat. If p hat times n and q hat times n are both greater than or equal to 5, then we can find the margin of error for a population proportion by the formula E equals ZC times the square root of p hat times q hat over n. Once you have your E, your interval becomes p hat minus E to p hat plus E. Like in the section in the chapter where we solved for the sample size for a given level of confidence for the mean, we can rearrange this formula for margin of error for proportion to solve for n, the sample size needed for a given level of confidence, margin of error, and sample proportion. If n ends up not being a whole number, always round up. And if p hat is not given, use a value of 0.5. Some students may be asked to construct confidence intervals for variance, which is sigma squared, or for standard deviation, which is sigma. For these problems, we will use the chi-square distribution. You can find a chi-square distribution table in the back of your book and also online, including in the Learning Success Center's LibGuide site. For these problems, we will, again, be using n-1 degrees of freedom. Note, the Greek letter chi looks like the letter x. It can be written out as chi, C-H-I. Funny story, for this video, I wanted to double check its pronunciation, and I found a website that gave the pronunciations of all the Greek letters. We use a lot of Greek letters in math, and it turns out we're not very good at pronouncing them. Sometimes we speak of angles, alpha, beta, and gamma. That beta in Greek is really pronounced more like vita. And you've used pi for some math classes. In Greek, that's the letter P. In statistics, we use the lowercase Greek letter mu to indicate population mean. Or should I say, me. It's the same for this letter. Our pronunciation is not quite right, but for math problems, we'll need to stay consistent. We'll stick with the chi. The chi-squared distribution is really a family of curves, one for each value of degrees of freedom. Note, these distributions are not symmetric. They are right-tailed skewed, though they get more symmetric for higher values of n. Because it is not symmetric, in these problems, we need to get two values from the chi-square table, called chi-L squared and chi-R squared. And unlike a z-table, when we use a chi-square table, we are looking up areas to the right. Here's an example. Let's say we have a sample size of 16, which is 15 degrees of freedom, and we want a level of confidence of 90%. What are the values of chi-L squared and chi-R squared? Like we did for critical z-scores, we start by knowing that 90%, or 0.9000, represents the middle of this chi-squared distribution. In this case, n-1, or 15 degrees of freedom. The whole area under the curve is 1, so the combined area in the tails is 0.1000. The area in each tail is half of that total, or 0.0500. Because the chi-squared table gives areas to the right, and the area in this left tail is 0.05, then on the table we will look to the column that shows area to the right of 1 minus 0.05, or 0.95. For 15 degrees of freedom, we get a chi-L square value of 7.261. Then, for the chi-R square position, we know it has an area in its right tail of 0.05, but since the chi-square table already gives areas to the right, we can simply use that column for 0.05 and again for 15 degrees of freedom to get a value of the chi-R square of 24.996. Once you have your chi-L square and chi-R square values, use these formulae to calculate the confidence intervals for variance or for standard deviation, depending on what you are asked to solve. Let us know if there was anything in this video that could be made more clear for future updates, and let us know if there are other videos you would like to see in this series. As always, check out our website for more information about services available in our Learning Success Center, or call, email, or stop by. Good luck, and I hope to see you this semester in the Learning Success Center.